So in this video clip, I'm going to go through the analytical Greeks for the Black-Scholes model, where we're using the derived formula. These generally are available in any of the textbooks and McDonald derivatives, John C. Hall, option futures, other derivatives, Espenhogue complete uh, formulas for derivatives, VBA. I leave the links to those textbooks underneath the video clip itself so that you'll be able to delve into the material a little deeper. Possibly important that you get a credible, reliable source for the formula. The Wikipedia page, in fact, this one is quite a good one, and the content here is reliable. So you can take a view, and it looks at the basic standard workhorse Greeks, and then the second order, third order as well. Now, importantly, in this instance, we will plan to take these formula and implement then in Python already. I've done that in VBA and in JavaScript for Google Sheets. But now I'm going to take a look at the Greeks where we implement those same formula in Python. So if we run our code cell here, you can see we're calculating initially D1 and D2, and then we are. So if we execute the code here for estimating D1, D2, and then get the probability density function, the Black-Scholes call, the delta for both the call and the put, gamma for call and put the same, Vega for call and put the same, theta and rho for call and put. And again, note that these estimates, this code is based on the analytical techniques developed above. So to observe a little bit more closely the operation of the code and that it satisfies previous estimations, I have the use case here where I take a standard set of benchmark numbers, execute, and for the call option, where the stock price is 100, K is 100, T is equal to 1 year, so the maturity on the option is 1 year, risk-free rate is 5%, dividend 0, and sigma is equal to 20%. We can observe directly here that for those parameter inputs, the value of the option is 1045, the put is 557, and we have the Greeks here for the call, and we can make a direct comparison with previous estimates I made using JavaScript. So if we copy our values here, Control V, Control C, and then go Control V, Control V, you can see that there is a correspondence between the estimates that we developed previously and here. So our code appears to be executing correctly. The Vega aligns, the theta for the call, -641, and the row and so on. Okay, so again, for the put option, we can execute and we can see some alignment as well. The put price 557, 557, and we have the delta for the put, the theta, and for row, and we can see a correspondence in each case as well. Okay, now for taking an example then from John C. Hall, we can look at from option futures other derivatives. There's an example there, and the video clip below runs through a manual estimation of that. So you might take a look at, so it just takes the problem as a use case, And for solving through for the particular parameter values that we have here, you can see how the formulas are implemented. So if we take S being equal to 0.8, K 0.81, T equal to 7 months, the rate of interest in the domestic jurisdiction 8%, the rate of interest in the foreign jurisdiction being 5, and sigma being 15%. If we input those parameter values and then execute to obtain the value of the Greeks, again, you'll see that the values largely accord with the ones produced in the video clip, right? So again, some corresponds as well. So you can check, in other words, we're doing a sort of a sanity check on our model just to verify the results are consistent. Again, another example I have here, and where the stock price is 42, K is 40, T is equal to 3 months, risk-free rate is 8%, dividend 0, volatility 30%. And when we execute, input those parameter values in and output our Greeks, the values obtained here are consistent with worked examples we used before. Okay, so how do we use these standard Greeks? And some interpretation for that, we'll consider the value of the Greeks in respect to various stock prices. And so a little bit what we're trying to develop here is to understand how each of the Greeks changes with respect to the underlying stock price. So we go back to the first use case where I've taken these parameter inputs. K is 100, P is equal to 1 year. The risk-free rate is 5%. I'll change Q back to 0 for the moment. Sigma is equal to 0.2. And then we generate the stock price as being a series of values between 50 and 150. So we take 100 uniform steps between 50 and 150. That is an array of stock prices. And we estimate the value for the delta calls, the delta of the puts, gammas, thetas of the calls, thetas of the puts, the vegas, the rows, the rows we estimate for the call and the rows we estimate for the puts. And we map out those in relation to varying stock prices. So if you like, we hold constant these parameters, but we allow the stock price to vary. And then we estimate the value of the options in sequence. So in effect, we're estimating the delta of the call and the put and the gamma, thetas, call and put, vegas, rotas for the call, rows for the put. And we do that for each of the stock prices that we incorporate into our arrays where we store the values of the Greek. So when we run the estimation here, we output a series of graphs. Let's scale that back a little bit. So we can see here each of the Greeks, the delta for the call, delta for the put. The gamma is the same for both call and put, but we sort of can see that as well because the delta is the change in the value of the call with respect to the change in the stock price. So in terms of when the call price, if we go back to our initial Black-Scholes-Merton model, and we look at the Black-Scholes parabola, we can see that when the stock price is low, again, we're using the same parameter inputs here, but to generate the Black-Scholes parabola with the Black-Scholes model, the delta represents the change in the value of the call with respect to the change in the value of the stock, or to what degree the call value changes for a given change in stock price. And initially it's zero, hardly any effect. The delta is zero. And then as we get closer to the exercise price, the um, value of the delta is increasing at an increasing rate. And then we observe that we sort of converge to one, or a value close to one. So we go from zero to one. And again, if we go back to our Greeks analytical techniques and then come down to the where we perform the estimation, option parameters, second order, that the slope here, the value here is represents the slope of the Black-Scholes parabola. So it's initially zero and goes to one. For a put option, it's initially -1 and goes to zero, but both, if we take the slope of delta, it produces gamma. So it's the second derivative. And initially, our slope here is zero. So the gamma slope is close to zero. And when we go deep in the money, our slope converges to one. So the slope of the delta is zero, and the delta is zero, increasing at an increasing rate, increasing at a decreasing rate. So we have a slope of zero, a slope of zero. There's correspondence between the two. But also note that the slope of the put, the put delta is the same as the slope for the call delta, thus producing the same gamma output. In the case of theta, if we run our code, we have for the call option, theta is negative. And for the put option, we have a positive region and then a negative region, right? So we've got to take the case of initially the call option here. Why is that negative? It's negative because as we reduce the time period, the value of the option is dropping. So with time decay, the value of the option is dropping. Now, if we put in a dividend yield that's positive, so we will observe in a second, if I change the dividend yield 0.5, let's say, we will get a positive region on the call theta. So if I make the dividend equal to 5% and rerun our graphs, you'll notice for the theta here, there is a positive region. So in the case of the call option here, take the call theta. For a deep in the money option, there is a positive theta, right? And that observation comes from the fact that as we increase uh, the uh, dividend, there is a bleed from the stock. So normally we're thinking the longer the life of the option, the more valuable the call option is. But if we if we make the dividend positive, it has a bleed effect on the value of the underlying asset. So we can observe actually there is it goes back to this relationship that we may have observed before when we're considering the parameters sensitivity, that it's unclear what the effect of increasing the time to maturity on the value of the European call and the value of the European put if the dividend is positive, right? There are instances where as we increase the time to expiration, the value of the European call can drop if the dividend is positive. If the dividend is zero, as we increase the maturity of the option, the value of the option goes up. Okay, so back to our standard Greeks. And our graphs. Then again for Vega, it's the same for both. And what we might also note is that Vega tends to increase as we get towards the exercise price of the option. The biggest effect of a change in the volatility will be observed close to the exercise. For Rho, again, as we increase the interest rate, right, if we take the case of the call option, if we consider the effect of increasing the interest rate, it's to discount more heavily the exercise, which increases the value um, of the option. So in the case of increasing, if I go back to the option properties, the parameter sensitivities, if you increase the interest rate, the value to call goes up, the value to put goes down. So from the stock option properties, from the option properties, we can see that the behavior of the Black-Scholes parabola in response to changes in the underlying is essentially what's being captured in terms of our Greek estimates, right? So, okay. So if we want to take that analysis a little bit further, then we would consider the higher order Greeks, right? And we would also consider perhaps the behavior of delta and gamma for different volatility. So we observe also, if we take the first graph in the sequence here, the delta, and we were to just isolate the delta call and then consider the effect of different volatilities. If we increase the volatility, what's the effect? What's the interaction between the delta and the volatility? So we can observe here that as we increase the volatility this is the value of the call delta relative to the stock price, so what we observed before, but now we've done it sequentially for different levels of volatility. And what we observe is as we increase the level of volatility, the delta becomes more linear and we go from a zero slope here to very quickly a very elevated delta when we're out of the money. So again, the exercise here is 100, but then the delta levels off much more quickly. We get to 1 or a value close to 1, but when the volatility is elevated, then the delta tends to be for the out of the money option to be way more elevated and for the in the money option to be less elevated. So with the low volatility, we don't do much most of the time. We are less responsive to changes, or the value of the call is less responsive to a change in the value to stock. But when the volatility is higher, changing the stock price actually will have a much more dramatic effect in terms of the value of the option for the out of the money option. Essentially, the chances of jumping into the in the money if you're out of the money is much higher. And when you're in the money, jumping to out of the money is also higher. So that has a depressing effect on the value of of the um, of the call. So the responsiveness, the delta, and the value of delta is obviously has interrelationships that are quite determining in terms of the overall effect on the delta. And for the gamma, we observe for the low volatility gamma, it's just tracking in essentially the slope here. So we're mainly zero, and we're zero in terms of the slope. But for the higher volatility, the slope is more elevated earlier and droops off in a more graduated fashion. and stays more elevated for a longer period of time. So the behavior of delta and gamma is very much conditioned by the volatility, and we'll observe that also for the impact of the maturity on the of the option as well. Okay, so let's leave that there.